For most of human history, the solar system felt isolated. 8 planets, countless moons, asteroids, comets, all born from the same ancient cloud of gas and dust more than 4.5 billion years ago. Everything here, everything we see, belongs to the same family. Until 2017. That was when something arrived that did not belong. A small, silent object drifting through our planetary neighborhood at extraordinary speed. It wasn't orbiting the sun. It wasn't bound to us. It had come from somewhere else, another star. We called it Oumuamua. Then, in 2019, another followed, 2I Borisov, a comet unmistakably foreign, carrying chemistry that formed in a different stellar system entirely. For the first time in history, we realize something profound. The solar system is not closed. It is not protected. It is not alone. And now, a third visitor has appeared. 3I Atlas, detected by automated sky surveys, scanning the darkness beyond Neptune. This object is moving in a trajectory that cannot be explained by anything born here. Its velocity is too high, its path too hyperbolic, its origin almost certainly interstellar. But this time, something feels different. Its brightness, its structure, its behavior. It does not resemble a typical comet. It does not resemble an asteroid either. And the more astronomers analyze its motion, the more one quiet realization settles in. This object may not be like the others. In tonight's calm exploration, we will trace the path of 3I Atlas from its discovery to its possible origin. We will explore what makes an object truly interstellar, how scientists calculate its trajectory, and why each new visitor reshapes our understanding of the galaxy around us. Not speculation, not exaggeration, just the real physics of an object that began its journey around another star and somehow found its way here. If you enjoy slow, immersive journeys through space and the mysteries of the universe, consider subscribing to Theories Before Sleep. Let's begin. There is a certain quiet ritual that happens every night. High above Earth's atmosphere, robotic telescopes sweep the sky. They do not sleep. They do not blink. They scan. Every point of light is catalogued. Every faint streak is measured. Every tiny shift in position is recorded and compared against millions of known objects. Most of what they find is familiar. Asteroids following predictable paths, comets returning on long elliptical orbits, fragments left over from the solar system's formation. But occasionally, something appears that does not behave, and it was during one of these routine scans that 3I Atlas was first detected. At first, it looked ordinary, a faint object, moving slowly against the background stars, barely distinguishable from the countless small bodies beyond Jupiter. But astronomy is not about what something looks like. It is about how it moves. Within hours of the first detection, additional observations were taken. The object's position was measured again, then again, and again. Each new measurement refined its trajectory. And slowly, something unusual began to emerge. Its path was not curved the way most solar system objects are. It wasn't looping around the sun on a long elliptical orbit. It wasn't bound. It was passing through. To understand why that matters, we have to talk about gravity. Every object born within the solar system is gravitationally tied to the sun. Even distant comets from the Oort cloud follow immense, stretched ellipses. They may take millions of years to return, but return they will. Their their orbits are closed. But 3I Atlas was different. Its orbit was hyperbolic. That means its path through space was open, a one-time passage. It would approach the sun, swing around it once, and then escape forever. No return, no repetition, just a brief visit. When astronomers calculate orbits, one of the most important numbers is eccentricity. If the eccentricity of an orbit is less than 1, the object is gravitationally bound. If it equals 1, it is just at the threshold of escape. If it is greater than 1, the object is not bound at all. For 3I Atlas, the eccentricity was clearly greater than 1. Not barely, decisively. That single number changed everything. It meant that before this object ever encountered the sun, it was already moving too fast to be captured. It had entered our solar system with excess velocity, carrying energy that did not originate here. It came from outside. But how far outside? To answer that, scientists calculate something called incoming velocity at infinity. This is the object's speed relative to the sun before solar gravity begins to significantly accelerate it. For ordinary comets, that value is essentially 0. They drift inward from the Oort cloud and gradually fall toward the sun. But interstellar objects arrive with speed already built in, like a traveler crossing the galaxy. Preliminary measurements of 3I Atlas suggested a significant inbound velocity, consistent with motion through the Milky Way itself, not the quiet outskirts of our own solar system. That was the second confirmation. This was not an escaped asteroid. It was not a comet perturbed by Jupiter. It was interstellar. Only twice before had we confirmed such an object. In 2017, Oumuamua stunned astronomers with its elongated shape and unexpected acceleration. In 2019, 2I Borisov arrived, clearly a comet, visibly shedding gas and dust as it approached the sun. Each one was different. And now, 3I Atlas joined that rare category. But something about this detection felt different from the beginning, because it was found earlier in its approach. And that matters. When Oumuamua was discovered, it was already on its way out, past its closest approach to the sun. We had missed the best opportunity to observe it. With 3I Atlas, astronomers had more time to measure its brightness, time to analyze its spectrum, time to look for activity. And this is where the mystery deepened. At first glance, it did not show the obvious coma of a comet. No dramatic cloud of gas expanding around it. No bright tail stretching away from the sun. But brightness can be deceptive. An object's apparent magnitude depends on distance, size, and reflectivity. Careful photometric analysis suggested that 3I Atlas might be larger than Oumuamua, or at least more reflective. And that raised new questions. Was it a rocky body, an icy one, a fragment of something much larger? To understand what 3I Atlas might be, we need to imagine its origin. Stars form in vast molecular clouds, cold regions where gravity slowly pulls gas and dust together. Around young stars, disks of material form. Inside these disks, planets assemble. But planetary systems are chaotic in their early stages. Gravitational interactions between forming planets can sling smaller bodies outward at extreme speeds. Some of those bodies never return. They become rogue fragments, drifting, unbound, wandering between stars. Over billions of years, the Milky Way becomes filled with such debris. The space between stars is not empty. It contains the scattered remnants of planetary systems that formed long before ours. Most of those fragments never come near another star again, but occasionally their paths intersect with another stellar neighborhood, like ours. And when they do, they briefly reveal themselves. One of the most fascinating aspects of 3I Atlas is that its trajectory allows astronomers to trace its motion backward, not to a precise star. That would require impossible accuracy over millions of years, but to a general region of the galaxy. By studying its velocity vector, its direction and speed relative to the Sun, scientists can determine how it was moving through the Milky Way before entering our system. Was it part of the thin disk? Did it originate from a star cluster? Was it traveling unusually fast compared to surrounding stars? Each measurement narrows possibilities, but perhaps the most profound realization is this: objects like 3I Atlas may be common. We just haven't been able to see them before. Until recently, our telescopes were not sensitive enough. Survey coverage was incomplete. Detection algorithms were slower. Now, with advanced sky surveys and automated tracking systems, we are finally able to notice faint objects moving quickly across the sky, which raises a possibility that is both humbling and extraordinary. Interstellar objects may pass through the solar system far more often than we thought. We are simply beginning to see them. In that sense, 3I Atlas is not just a scientific curiosity, it is a preview, a glimpse into a future where interstellar astronomy becomes routine, where instead of studying distant exoplanets indirectly, through tiny dips in starlight, we examine fragments of those systems directly as they pass through ours, because that is what 3I Atlas represents, a piece of another solar system, older than our civilization, possibly older than Earth's oceans, carrying within it chemical signatures forged around a different star. And as it approaches the Sun, the real investigation begins. Will it develop cometary activity? Will sunlight heat hidden ices and release gas? Will spectroscopy reveal exotic chemistry? Or will it remain quiet, a dark, rocky relic drifting silently past? The answers will not come dramatically. They will come slowly, one observation at a time. A new brightness curve here, a spectral line there, a slight deviation in trajectory. Astronomy is patient, and interstellar visitors demand patience. Because once 3I Atlas passes beyond the orbit of Jupiter again, it will never return. It will continue its journey around the galaxy, perhaps passing near another star millions of years from now, perhaps drifting alone for eternity. But for this brief moment in cosmic time, it is here, crossing the region we call home. And that fact changes something subtle but profound. It reminds us that the solar system is not isolated. It is part of a much larger exchange. Matter moves between stars. Fragments travel unimaginable distances. The galaxy is dynamic, alive with motion. In the next part of our journey, we'll explore what 3I Atlas might be made of, how astronomers determine composition from light alone, and whether this third interstellar visitor could challenge what we think we understand about planetary formation itself. Because sometimes the smallest objects carry the biggest stories. And 3I Atlas may be one of them. When an object comes from another star system, we cannot visit it. We cannot land on it. We cannot sample its surface. We cannot drill into its interior. All we have is light. And yet, from light alone, astronomers can uncover astonishing detail. The shape of an orbit tells us where 3I Atlas has been, but the light it reflects and possibly emits tells us what it is. Every time sunlight strikes the surface of an object, part of that light is absorbed and part of it is reflected back into space. The reflected light carries subtle fingerprints, tiny distortions, missing wavelengths, faint lines in a spectrum that reveal the chemistry of the material it touched. This is spectroscopy, one of the most powerful tools in astronomy. When astronomers pointed spectrographs toward 3I Atlas, they were not just measuring brightness. They were splitting its light into a rainbow, searching for patterns. If the object contained water ice, certain wavelengths in the infrared would be absorbed. If it contained carbon-rich compounds, its spectrum might appear reddish. If it were metallic, the reflectance curve would look different again. These measurements are delicate. Interstellar objects are faint. They move quickly across the sky. Observations must be precise and often brief, but even early data can hint at structure. With Oumuamua, astronomers detected a reddish surface, consistent with organic rich material that had been exposed to cosmic radiation for millions of years. It appeared dry, inactive, almost asteroid-like, yet its slight non-gravitational acceleration suggested outgassing, possibly hydrogen or some volatile substance invisible to telescopes. With 2I Borisov, the story was clearer. It behaved like a classic comet. It developed a visible coma. Spectra revealed water vapor, carbon monoxide, and dust, familiar cometary materials, but formed around another star. Now, with 3I Atlas, scientists are asking, does it resemble Borisov, icy and active? Or is it closer to Oumuamua, dark and enigmatic? Or something entirely new? Initial photometric measurements, tracking how its brightness changes over time, provide the first clues. If an object rotates, its brightness fluctuates. A long, irregular shape will reflect more light when its broadside faces us and less when it turns edge on. These brightness variations can reveal rotation periods and rough shape estimates. If 3I Atlas shows strong variability, it might be elongated or irregular. If it remains steady, it could be more spherical. Early data suggests moderate variability, but not extreme. Nothing as dramatic as the extreme light curve observed with Oumuamua, which changed brightness by a factor of 10. That alone suggests 3I Atlas may not be as elongated, but brightness tells only part of the story. As it approaches the sun, solar radiation intensifies, surfaces warm, subsurface ices may begin to sublimate, turning directly from solid to gas. If that happens, a faint coma could develop. Even a thin envelope of gas can dramatically change an object's appearance. And here is where timing becomes critical. Because we detected 3I Atlas earlier in its approach, astronomers can monitor it gradually. They can watch for the moment when activity begins, if it begins at all. If gas jets emerge, they may produce slight accelerations, altering its trajectory by tiny amounts. These deviations can be measured, and from them, scientists can estimate mass and density. Density is important. A dense, rocky object behaves differently from a porous, icy one. If 3I Atlas is loosely bound rubble, a fragile aggregate of material, it might fragment under solar heating. If it is compact and metallic, it may remain stable. Each possibility tells a different story about its origin. In planetary systems around other stars, small bodies form in protoplanetary disks, swirling disks of gas and dust. Temperature gradients determine what materials condense where. Close to a star, only metals and silicates survive. Farther out, ices can freeze. Water, methane, ammonia. If 3I Atlas formed near its original star, it might be rocky. If it formed in the colder outskirts, it might be icy. But there is another possibility. It could be a fragment ejected during a violent planetary interaction. Imagine a young star with giant planets forming. As these massive bodies migrate, they gravitationally scatter smaller objects. Some are thrown inward, others are ejected entirely from the system. In that chaos, collisions are common. Fragments can form, and 3I Atlas may be one of those fragments, a survivor of ancient instability. Another method astronomers use to study composition is color indexing. By comparing brightness in different wavelength filters, blue, green, red, they can infer surface properties. A red slope in reflectance often suggests complex organic molecules formed by radiation processing. A neutral color suggests fresher or rockier material. Early reports indicate that 3I Atlas may have a slightly reddish hue, though not extreme. That places it somewhere between asteroid-like and comet-like. But the real breakthrough may come from infrared observations. Infrared light penetrates dust and reveals thermal properties. By measuring how much heat 3I Atlas emits, astronomers can estimate its size independently of reflectivity. An object that appears bright could either be large and dark or small and highly reflective. Thermal modeling separates those possibilities. If 3I Atlas turns out to be larger than Borisov, perhaps several kilometers across, that would be remarkable. It would imply that large interstellar objects survive long journeys between stars. But survival in interstellar space is not trivial. Between stars, temperatures are near absolute zero. Cosmic rays bombard surfaces. Over millions of years, radiation can alter chemical bonds, darken surfaces, and deplete volatiles. Some models suggest that only certain types of objects survive intact. If 3I Atlas shows preserved ices, it may not have traveled for billions of years. If it appears heavily processed, its journey may have been far longer. This leads to one of the most intriguing questions. How old is it? Not just in years since formation, but how long it has wandered alone. By analyzing isotopic ratios, if measurable, scientists can compare its chemistry to known stellar populations. Does it resemble material from metal-rich stars or older, metal-poor populations? Even if we cannot trace it to a specific star, we may narrow its birthplace to a galactic region. And there is something quietly extraordinary about that. Because when we study 3I Atlas, we are not merely observing an object, we are sampling the galaxy. Each interstellar visitor expands our dataset. Before 2017, interstellar objects were theoretical. Now we have 3. And with each one, patterns may emerge. Perhaps most are icy, perhaps most are rocky. Perhaps their size distribution reveals something about planetary system dynamics across the Milky Way. In that sense, 3I Atlas is not an isolated curiosity. It is part of a growing statistical sample. And as surveys improve, especially with next-generation observatories, we may detect dozens more in coming decades. Some may be smaller, some larger, some stranger. There is even discussion of future missions, rapid response spacecraft capable of intercepting an interstellar object during its passage. It would require extraordinary planning, short notice, high velocity, but the scientific reward would be immense. For now, we remain observers, watching from Earth as 3I Atlas approaches, measuring photons, analyzing spectra, tracking its motion against distant stars. And with each observation, we refine our understanding. Is it active? Is it inert? Is it fragile? Is it ancient? The truth will not reveal itself all at once. It will emerge slowly, data point by data point, light curve by light curve, until a clearer picture forms. And when it does, 3I Atlas will no longer be just the third interstellar object. It will be something more specific, a comet from another system, a rocky shard from a distant planet-forming disk, a relic of a long-destroyed world. In the next part of our journey, we will explore what happens as 3I Atlas reaches Perihelion, its closest approach to the Sun, and how that moment may determine whether it becomes spectacular or remains quietly mysterious. Because sometimes the most revealing moment in an object's life is when it feels the heat of a new star for the very first time, and that moment is coming. As 3I Atlas continues its inward journey toward the Sun, everything begins to change. Far from the Sun, beyond the orbit of Jupiter, the environment is quiet and cold. Solar radiation is weak. Surface temperatures remain extremely low. Any volatile materials, water ice, carbon monoxide, methane, remain frozen solid. The object drifts in darkness, reflecting only a faint fraction of sunlight. But as it approaches the inner solar system, solar energy increases rapidly. Radiation intensity follows the inverse square law. Cut the distance in half, and sunlight becomes 4 times stronger. By the time 3I Atlas reaches the region between Mars and Earth, the heating will be dramatically different from anything it has experienced during its long journey between stars. If 3I Atlas contains volatile ices beneath its surface, this heating will awaken them. Ice does not melt in the vacuum of space. It sublimates. It transitions directly from solid to gas. Gas escaping from beneath the surface can form jets, pushing dust outward and creating a faint coma around the object. This is what defines a comet. The development of a coma depends on composition, structure, and internal temperature. If 3I Atlas formed in the outer regions of its original star system, it may contain abundant ices. In that case, astronomers may soon observe a growing cloud of gas and dust expanding around it. If, however, it formed closer to its star, or has already lost much of its volatile material during its long interstellar journey, it may remain largely inactive. This distinction is crucial because the presence or absence of activity reveals the environment where it was born. As solar heating increases, astronomers carefully monitor its brightness. A comet brightens not only because it approaches the Sun, but because the coma reflects additional sunlight. A sudden increase in brightness beyond what orbital geometry predicts may signal the onset of sublimation. Spectroscopic instruments are then trained on it immediately. If water vapor is released, its spectral lines will appear in the infrared. If carbon monoxide or carbon dioxide is present, those signatures may be detected as well. These molecules tell a story. Water ice suggests formation beyond the snowline of its original system, a region far enough from the star for water to freeze. Carbon monoxide, which freezes at much lower temperatures, indicates formation even farther out. By measuring relative abundances, scientists can compare 3 Eye Atlas to comets from our own solar system. If its chemical ratios differ significantly, it may reflect a different protoplanetary disk chemistry. But heating also introduces risk. If 3I Atlas is structurally weak, more a loosely bound aggregate than a solid rock, it may not survive close approach intact. Comets in our solar system often fragment when they pass too close to the sun. Solar heating causes internal pressure to build as trapped gases expand. Fractures can propagate. Pieces can break away. If 3I Atlas begins to fragment, telescopes may detect multiple components traveling together. Fragmentation would reveal its internal strength. A solid rocky body would likely remain intact. A porous, icy object might crumble. Perihelion, the point of closest approach to the sun, is the defining moment. At perihelion, temperature peaks. Thermal stress is greatest. Outgassing, if present, becomes strongest. It is also the moment when trajectory perturbations become measurable. Jets of escaping gas produce thrust. Even tiny forces, sustained over days, can alter the object's path slightly. Astronomers compare observed positions to purely gravitational models. If deviations appear, they infer non-gravitational acceleration. This was one of the puzzles of Oumuamua. It accelerated slightly more than expected. The most plausible explanation was outgassing, but no visible coma was detected. This led to speculation about unusual composition, perhaps hydrogen ice or extremely fine dust emission invisible to telescopes. With 3I Atlas, scientists are prepared. Multiple observatories coordinate measurements. Optical telescopes measure brightness. Infrared instruments track thermal emission. Radio telescopes may search for molecular lines. Every dataset matters. If 3I Atlas behaves like Borisov, developing a clear coma and tail, its nature will be more straightforward. It will confirm that icy interstellar comets are not rare. If it remains dark and inert, it may suggest that rocky interstellar fragments are equally common, or it may fall somewhere between, displaying weak activity, hinting at mixed composition. One subtle measurement involves rotational changes. Outgassing jets can act like thrusters. If gas escapes unevenly across the surface, it can alter spin rate. By measuring changes in brightness periodicity, astronomers can detect acceleration or deceleration in rotation. Rapid spin could lead to breakup if centrifugal force exceeds structural cohesion. Monitoring rotation is therefore essential near perihelion. Another factor is surface temperature distribution. An object that rotates slowly will heat unevenly. One hemisphere may face the sun for extended periods, leading to thermal stress. Cracks may form. Dust layers may shift. Thermal modeling allows astronomers to simulate internal heating. Heat penetrates only a limited depth during short perihelion passage. The deeper interior may remain cold. This means some volatiles may never sublimate. In fact, 3I Atlas may leave the solar system still carrying pristine material untouched by sunlight. That material will never be studied directly. It will continue drifting through interstellar space, perhaps for millions of years. As it rounds the sun, its velocity increases dramatically. Gravitational acceleration converts potential energy into kinetic energy. At perihelion, it reaches maximum speed. After that point, it begins to climb outward again, slowing gradually as it escapes. But unlike bound comets, it will not return. Its outbound trajectory will carry it beyond Jupiter, beyond Neptune, past the Kuiper belt, and eventually beyond the gravitational dominance of the Sun. Within decades, it will be too faint to observe. Within centuries, it will be indistinguishable from background stars. And yet, during its brief passage, it provides a rare opportunity. Interstellar objects offer something unique: physical samples of other planetary systems without leaving home. Exoplanets are detected indirectly. Their atmospheres are inferred from faint absorption lines during transits. Their surfaces remain unknown. But 3I Atlas is tangible in a way distant exoplanets are not. It is here, moving through our system, subject to our instruments. If future technology improves rapid response capabilities, perhaps one day spacecraft could intercept such objects. Concept studies already exist for missions that could launch on short notice to chase interstellar visitors. High-speed propulsion, gravity assists, and advanced guidance systems would be required. But for now, observation from afar must suffice. As perihelion approaches, public attention often grows. Interstellar objects capture imagination. They raise questions about origin, frequency, and even speculative ideas about artificiality. But the scientific approach remains grounded. Measure orbit, measure brightness, measure spectrum, model composition, compare with previous visitors. No extraordinary assumptions are needed. Physics explains hyperbolic trajectories. Planet formation theory explains ejection. Spectroscopy explains composition. What makes 3I Atlas extraordinary is not that it defies physics. It is that it confirms it. Planetary systems are dynamic. They eject material. The galaxy is full of wandering debris, and occasionally that debris crosses our path. If 3I Atlas survives perihelion intact, it may reveal subtle changes in surface reflectivity. Solar heating can remove outer radiation process layers, exposing fresher material beneath. Color indices may shift slightly before and after perihelion. Comparing inbound and outbound spectra may reveal such changes. If fragmentation occurs, smaller fragments may display different activity levels depending on internal composition. Each scenario provides data. Each outcome refines models of interstellar population. Perhaps most importantly, 3I Atlas helps estimate how common such objects are. If 3 have been detected within a few years, detection bias suggests many more pass unnoticed. The true interstellar object density in the galaxy may be substantial. Future surveys, especially more sensitive sky-scanning telescopes, will likely increase detection rates. One day, we may detect interstellar objects weekly. For now, each one is an event. As 3I Atlas reaches perihelion, telescopes around the world remain focused. Its brightness peaks. Its structure reveals itself as much as physics allows. Then it turns outward. Solar radiation decreases. Any coma fades. Activity subsides. And gradually, it becomes a faint moving dot once more. It will leave with slightly altered surface chemistry, slightly warmer interior layers, perhaps a few fragments shed behind it, but fundamentally unchanged in identity. A traveler from another star, having visited ours and continuing onward. Its passage reminds us that the solar system is not sealed. It is part of a dynamic galactic exchange. Matter moves. Systems interact indirectly through wandering fragments. And sometimes, those fragments allow us to study another star's history without ever leaving home. As 3I Atlas begins its outbound journey, one thing becomes clear. It is not just a third interstellar object. It is evidence. Evidence that planetary systems across the Milky Way are not isolated islands. They are contributors to a vast, slow-moving current of material, and occasionally that current flows through us, quietly, briefly, leaving behind data and perspective before disappearing back into the dark between stars. Long before 3I Atlas ever approached our Sun, long before Earth even formed its oceans, this object already existed somewhere else, not here, not within our solar system, but in another planetary system orbiting another star somewhere within the Milky Way galaxy. To understand where it might have come from, astronomers begin by studying its motion through space. Every object carries with it a record of its journey. Velocity is not just speed, it is direction. And when scientists measure both, they can trace the object's path backward through time. But tracing an interstellar object backward is extremely difficult. Stars move. The galaxy rotates. Gravitational interactions accumulate over millions of years. Even small uncertainties in velocity multiply dramatically when projected across vast distances and long timescales. If we attempt to rewind the motion of 3I Atlas for millions of years, the path quickly becomes uncertain. It spreads like a fan across possible trajectories. After tens of millions of years, its origin becomes almost impossible to pinpoint precisely. Yet even if we cannot identify the exact star system that ejected it, we can still learn something about its birthplace. Astronomers compare the object's motion with the general motion of stars in the Milky Way. Most stars in our galaxy belong to a structure called the thin disk, a vast rotating layer where stars orbit the galactic center in roughly similar directions. If 3I Atlas moves with a velocity similar to nearby stars in the disk, it may have originated from a typical planetary system, not too different from our own. But if its motion is unusual, faster, or in a different direction, it could suggest a more exotic origin. Perhaps it was ejected from a young star cluster where gravitational encounters were violent and chaotic. Star clusters are dynamic environments. Hundreds or thousands of stars form together within dense clouds of gas. During their early years, these stars pass relatively close to one another. Their planetary systems interact gravitationally in subtle ways. When giant planets form within these systems, they often migrate. Their orbits shift as they interact with the surrounding disk and with each other. In many cases, this migration destabilizes smaller bodies, like asteroids and comets. Some of these bodies fall inward toward their stars. Others are flung outward with tremendous speed. When an object is ejected from a planetary system, it escapes the gravitational pull of its star and becomes a rogue traveler. It drifts through interstellar space, orbiting the center of the galaxy independently. Over billions of years, the Milky Way accumulates enormous numbers of these wanderers. Some estimates suggest there may be trillions of interstellar objects drifting between stars. Most of them are small, most are dark, and most will never encounter another planetary system again. But occasionally, one crosses paths with a star like ours. And when it does, it briefly becomes visible. The discovery of 3I Atlas raises another intriguing possibility: that planetary systems throughout the galaxy eject far more material than we once believed. Our own solar system may have done the same. During the early history of the solar system, the giant planets Jupiter, Saturn, Uranus, and Neptune did not always occupy their current orbits. According to models of planetary migration, these massive worlds shifted positions dramatically as they interacted with leftover debris from planet formation. Jupiter, in particular, played a powerful role. With its immense gravity, Jupiter scattered countless icy bodies outward into the distant Oort cloud. Many were captured into long-period orbits around the Sun, but others were accelerated to escape velocity and expelled entirely from the solar system. Those objects are now interstellar too. Somewhere in the galaxy, fragments born near the young Sun may now be drifting between stars, just like 3I Atlas. In this way, interstellar objects represent a kind of cosmic exchange. Planetary systems continuously lose material, and sometimes they gain it if a passing fragment becomes temporarily captured. But capture is rare. For an object moving at interstellar speeds, the Sun's gravity alone is usually insufficient to trap it. The object must lose energy somehow, perhaps through interactions with planets or by passing through gas. Such circumstances are extremely uncommon. That is why 3I Atlas will not remain here. It is only passing through. Another mystery concerns the age of interstellar objects. If 3I Atlas was ejected billions of years ago, it has spent most of its existence in deep space. In that environment, temperatures hover just a few degrees above absolute zero. Cosmic rays slowly bombard exposed surfaces. Over immense timescales, this radiation can alter chemical structures, darken surfaces, and form complex organic molecules. Astronomers sometimes refer to this process as space weathering. If 3I Atlas has traveled for hundreds of millions or billions of years, its outer layers may have been heavily modified by radiation. This could explain reddish colors detected in some interstellar objects. But if its surface appears relatively fresh, it might suggest a shorter journey. Perhaps it was ejected more recently from a young planetary system. Young star systems are particularly violent places. Giant planets often form quickly and migrate through the disk, scattering debris everywhere. In the early millions of years after formation, planetary systems can eject huge numbers of small bodies. If 3I Atlas originated from such a system, it might be much younger than the solar system. Another clue comes from the distribution of interstellar objects detected so far. Oumuamua appeared asteroid-like but exhibited strange acceleration. Borisov behaved like a classic comet. And now 3I Atlas may represent yet another category. Each discovery adds to a small but growing sample. From these samples, astronomers attempt to estimate how common different types of interstellar objects are. Are icy comet-like bodies the majority? Or are rocky fragments more typical? The answer reveals something about the architecture of planetary systems across the galaxy. If most interstellar objects resemble comets, it suggests that outer icy regions of planetary systems are the primary source of ejected material. If rocky objects dominate, then inner planetary systems may contribute more fragments than previously thought. Another possibility is that many interstellar objects are fragments of larger collisions. Planet formation is messy. Young planets collide, asteroids shatter. Entire worlds may be disrupted during gravitational encounters. Such events produce debris fields that can later be ejected into interstellar space. In this sense, 3I Atlas might not simply be a leftover building block of a planet. It might be a fragment of a world that once existed, Perhaps a planetesimal broken apart by collision. Perhaps a piece of a moon destroyed long ago. There is something deeply humbling in that idea. A fragment born under another star, traveling through darkness for millions of years, now passing silently through our sky. And while we cannot yet determine its exact origin, each observation narrows the possibilities. As telescopes continue to monitor 3I Atlas, astronomers refine its orbit and velocity. With enough data, they can estimate its incoming direction relative to the motion of nearby stars. If its velocity closely matches the motion of local stellar populations, its birthplace may have been within our region of the galaxy. If its speed is unusually high or its direction unusual, it may have originated from a different region entirely. But even if we never identify its parent star, the existence of 3I Atlas tells us something profound about our galaxy. Planetary systems are not isolated worlds forming quietly and remaining stable forever. They are dynamic. They eject material. They scatter fragments across interstellar space. The Milky Way is filled with debris from countless planetary systems. And sometimes those fragments visit us. In the next part of our journey, we will explore what scientists hope to learn before 3I Atlas disappears again into the darkness beyond Neptune, and why each interstellar visitor may eventually change the way we study other planetary systems across the galaxy. The passage of an interstellar object through the solar system is brief. On cosmic timescales, it is almost nothing. 3I Atlas may have spent millions or even billions of years traveling through the dark spaces between stars. Yet its visit to our solar system will last only a short moment, a few months of careful observation before it fades again into the distance. For astronomers, this short window is both exciting and frustrating. Exciting because each new interstellar object offers rare information about planetary systems beyond our own. Frustrating because the opportunity disappears quickly. Once 3I Atlas moves beyond the orbit of Jupiter again, sunlight becomes too weak for detailed observations. The object will dim rapidly. Even the largest telescopes will eventually lose it. That means scientists must learn as much as possible while it is still visible. One of the most important measurements involves determining its exact size. At first glance, this might seem simple. If we can see the object, surely we can measure how large it is. But in reality, it is more complicated. Telescopes do not see the physical surface of small distant objects. Instead, they detect reflected sunlight. A bright object could be large and dark, or small and highly reflective. To separate these possibilities, astronomers combine optical observations with thermal measurements. Infrared telescopes measure how much heat the object emits. Warmer objects emit more infrared radiation. By comparing reflected sunlight and thermal emission, scientists can estimate both size and surface reflectivity, known as albedo. If 3I Atlas turns out to be only a few hundred meters across, it would resemble many typical comets. If it is several kilometers wide, it would be a far more substantial body, possibly representing a large fragment from another planetary system. Determining the size also helps estimate mass. Mass matters because it influences how the object responds to forces like outgassing jets or solar radiation pressure. Another key measurement involves rotation. Every small body in space rotates. Some spin slowly, completing one rotation every few days. Others spin rapidly, turning once every few hours. Rotation affects how sunlight heats the surface. It also influences structural stability. If an object spins too quickly, centrifugal forces can overcome gravity and cause it to break apart. Astronomers measure rotation by tracking changes in brightness. As an irregular object spins, different surface areas reflect different amounts of light toward Earth. These brightness variations create a repeating pattern called a light curve. By analyzing this pattern, scientists can determine rotation period and sometimes even infer rough shape. If 3I Atlas rotates rapidly, it may be structurally strong. If it rotates slowly, it may be a loosely bound rubble pile held together mostly by weak gravity. But rotation alone does not tell the whole story. Astronomers are also interested in how the object's rotation changes over time. If jets of gas escape from its surface, they can act like tiny thrusters. Over days or weeks, these jets can gradually accelerate or slow the rotation. Detecting such changes provides direct evidence of outgassing activity. Another important investigation involves searching for a tail. Most comets develop tails when they approach the Sun. There are actually two kinds of comet tails. The first is a dust tail. Dust particles released from the surface are pushed away by sunlight. They form a broad curved tail that reflects sunlight. The second is an ion tail. When gas molecules escape and become ionized by solar radiation, the solar wind carries them away from the Sun, forming a long straight tail that glows faintly. If 3I Atlas develops either type of tail, telescopes will capture it. The presence of a tail would confirm volatile materials beneath the surface. However, it is also possible that any activity may be subtle. Interstellar objects may have lost some of their most volatile ices during their long journeys through space. Over millions of years, cosmic radiation can slowly heat and modify surface layers. This process can create a protective crust that traps remaining volatiles deeper inside. If that is the case, 3I Atlas might display only weak or delayed activity. Even so, sensitive instruments can still detect faint gas emissions. Spectroscopy once again becomes essential. By analyzing the wavelengths of light emitted by escaping gas, scientists can identify molecules present in the coma. Water vapor produces characteristic spectral lines. So do carbon monoxide, methane, ammonia, and various organic compounds. Each molecule provides clues about formation conditions. Different protoplanetary disks contain different chemical environments. Temperature gradients, radiation levels, and disk composition all influence which materials condense and where. By comparing 3I Atlas chemistry with solar system comets, scientists can identify similarities and differences. If its chemical composition matches our comets closely, it suggests that planet formation processes across the galaxy may follow similar patterns. If its chemistry is very different, it could reveal alternative pathways of planetary formation. Another intriguing measurement involves dust grains. When dust is released into space, telescopes can analyze how it scatters light. The scattering pattern depends on particle size and composition. Fine dust produces smooth, diffuse halos. Larger grains produce brighter and more structured tails. Polarization measurements. Studying how light waves vibrate after reflecting off dust provide even more information about particle shape and composition. From these subtle signals, astronomers can infer whether the dust grains resemble those found in our own comet tails. But perhaps the most exciting possibility involves detecting organic molecules. Organic chemistry is common in space. Complex carbon-based molecules have been found in meteorites, comets, and interstellar clouds. If 3I Atlas carries similar compounds, it would support the idea that organic chemistry is widespread throughout the galaxy. That does not mean life exists elsewhere, but it suggests that some of the ingredients necessary for life may be common. In fact, some scientists believe that interstellar objects may play a role in distributing organic materials between planetary systems. During the early stages of planetary formation, fragments ejected from one system could potentially deliver organic compounds to another. Such exchanges would be rare, but over billions of years they could occur. Whether or not that has happened in our galaxy remains unknown, but objects like 3I Atlas remind us that planetary systems are not completely isolated. Material can move between them. As observations continue, astronomers also refine estimates of the number of interstellar objects in the galaxy. The detection of 3 such visitors within just a few years suggests they may be far more common than previously thought, most likely pass unnoticed. Many are probably too small or too dark to detect. Others pass through regions of the sky where telescopes are not currently scanning. But new observatories are changing this. One of the most important upcoming facilities is the Vera C. Rubin Observatory. With its enormous camera and wide field of view, this telescope will scan the entire visible sky repeatedly, detecting faint moving objects with unprecedented sensitivity. When it becomes fully operational, astronomers expect the discovery rate of interstellar objects to increase dramatically. Instead of discovering one every few years, we may detect several each year. With a larger sample, scientists will begin to understand the true population of interstellar debris. They will learn whether most objects are icy or rocky. They will measure typical sizes and velocities. They will compare chemical compositions. In time, interstellar astronomy may become a new branch of planetary science. Instead of studying only objects formed around our sun, scientists will study fragments of many different star systems. Each one carries a story. Each one reveals something about the diversity of planetary systems across the Milky Way. For now, 3I Atlas is the latest chapter in that story. As it continues its journey through the solar system, telescopes remain fixed on it. Every observation adds a piece to the puzzle. Every measurement deepens our understanding, and slowly, the picture becomes clearer. Not just about this one object, but about the galaxy itself, and the countless worlds that form within it. For most of human history, the idea of objects traveling between stars belonged more to imagination than to science. The distances between stars are enormous. Even the closest neighboring systems lie trillions of kilometers away. The space between them seems empty and silent. Yet modern astronomy has revealed that this space is not completely empty. It contains wandering fragments, debris left behind by the violent process of planetary formation. When planets form around young stars, chaos is unavoidable. Massive bodies migrate, orbits shift, collisions occur. Entire regions of debris are destabilized. Many smaller objects are thrown outward at tremendous speeds. Some fall back toward their stars. Others are ejected completely. Once they escape the gravity of their parent star, they become interstellar travelers. They drift through the galaxy, sometimes for millions of years, sometimes for billions, and occasionally they pass near another star. 3i Atlas is one of those travelers, but its discovery represents more than a single object. It marks the beginning of a new era of astronomy. For centuries, astronomers studied only objects born within our own solar system. Every asteroid, every comet, every planet we observed shared a common origin around the Sun. Now that has changed. With the discovery of multiple interstellar visitors, scientists are beginning to study material from entirely different planetary systems. In effect, the galaxy is sending us samples, and with improved technology, we will soon detect many more. The key to this future lies in better sky surveys. Modern astronomy relies heavily on automated observatories that continuously scan the sky for moving objects. These telescopes capture enormous images of the night sky and compare them with earlier observations. If a faint point of light has shifted position slightly, computer algorithms flag it as a potential moving object. This is how objects like 3i Atlas are discovered. But current surveys still have limitations. They cannot see extremely faint objects. They cannot monitor the entire sky continuously, and they cannot always detect objects moving very quickly relative to background stars. The next generation of observatories will change that. Among the most anticipated is the Vera C. Rubin Observatory in Chile. Its massive telescope and advanced camera will photograph the entire visible sky every few nights. Each image will contain billions of stars and galaxies, and hidden among them, moving slowly across the field, will be asteroids, comets, and perhaps many interstellar objects. The Rubin Observatory survey, known as the Legacy Survey of Space and Time, will generate an unprecedented stream of data. It is expected to discover millions of new solar system objects, and almost certainly many new interstellar visitors. With a larger sample of these objects, astronomers will begin to answer fundamental questions. How common are interstellar objects? How large are they? What are they made of? Do they resemble comets from our own solar system, or are they fundamentally different? Right now, the sample size is too small to draw strong conclusions. 3 objects are intriguing. 30 would be informative. 300 would transform our understanding. Each new discovery will add to a growing database. Scientists will compare orbital speeds, directions, compositions, and sizes. Patterns will emerge. Perhaps most interstellar objects come from outer icy regions of planetary systems. Perhaps rocky fragments from inner systems are more common. Perhaps collisions between planets generate vast numbers of fragments. Or perhaps something entirely unexpected will appear. Another exciting possibility involves spacecraft missions. Right now, all observations of interstellar objects are made from Earth or from telescopes in orbit. But what if we could send a spacecraft to intercept one? Several mission concepts have already been proposed. One of the main challenges is timing. Interstellar objects move extremely fast relative to the Sun. By the time we detect one, it may already be approaching the inner solar system at high speed. Launching a spacecraft quickly enough to catch it requires extraordinary planning. One idea involves keeping a spacecraft ready in orbit around the Sun, waiting for a target. Once a suitable interstellar object is detected, the spacecraft could rapidly adjust its trajectory using powerful propulsion systems. Another idea uses gravity assists by passing near planets such as Jupiter. A spacecraft can gain additional speed and redirect its path toward a target. These techniques have been used successfully in past missions to explore the outer solar system. However, intercepting an interstellar object would require even greater precision. The relative speed between the spacecraft and the target could exceed tens of kilometers per second. Even a brief flyby could yield enormous scientific value. A spacecraft could photograph the object at close range. It could measure surface composition directly. It could analyze dust particles escaping from the object. Instruments could detect magnetic fields, chemical signatures, and perhaps even isotopic ratios. Such measurements would provide insights impossible to obtain from Earth. In effect, we would be exploring material formed around another star. Although such missions remain challenging, the idea is gaining momentum. As more interstellar objects are detected, the chances of planning a successful interception increase. In time, space agencies may design dedicated missions for this purpose. Another intriguing possibility is temporary capture. While most interstellar objects pass through the solar system too quickly to be captured, certain rare trajectories may allow a temporary gravitational capture by the Sun and planets. If an object passes near Jupiter at just the right speed and angle, Jupiter's gravity could slow it enough to place it into a temporary orbit around the Sun. Such captured objects might remain within the solar system for decades or centuries before escaping again. If that ever happens, astronomers would have far more time to study such an object, perhaps even send spacecraft to investigate it closely. Some researchers have already begun searching for such temporarily captured interstellar visitors among known asteroid populations. So far, none have been definitively identified, but the possibility remains. Even without capture, the study of objects like 3I Atlas has already expanded our understanding of planetary formation. For decades, scientists suspected that planetary systems eject large amounts of material during their early evolution, but there was little direct evidence. Now we are beginning to see the results of that process. Each interstellar object represents a fragment of another planetary system's past. Some may have formed in icy outer regions. Others may have formed closer to their stars. Some may be collision fragments. Others may be intact primordial bodies. The diversity of these objects will reveal the diversity of planetary systems across the galaxy, and that diversity is likely enormous. Astronomers have already discovered thousands of exoplanets orbiting distant stars. Some are massive gas giants orbiting extremely close to their stars. Others are rocky worlds orbiting within habitable zones. Some systems contain multiple giant planets in tightly packed orbits. Others appear quiet and stable. If planetary systems differ so dramatically, the debris they eject will also differ, and interstellar objects may carry the chemical and physical fingerprints of those differences. In this way, objects like 3I Atlas become messengers. They carry information across unimaginable distances. They bring clues about worlds we may never see directly. Each time one enters our solar system, it gives us a brief opportunity to examine material born around another star. And although these visitors depart quickly, their scientific legacy remains. The data collected from 3I Atlas will continue to be analyzed for years. New observations will refine models of its structure and composition. Future discoveries will allow comparisons. Gradually, a new field of astronomy will emerge. one focused not on planets themselves, but on the fragments they leave behind. Fragments that travel through the galaxy, occasionally crossing our path and reminding us that the solar system is not an isolated island. It is part of a vast galactic network, a network where matter moves, systems interact indirectly, and ancient fragments wander endlessly between stars. 3. I-Atlas is only one of them, but it is one we have the chance to study. And that chance is enough to change how we see our place in the universe. Long before 3 I-Atlas ever appeared in our telescopes, long before its faint light moved slowly across our sky, it had already traveled farther than any object humanity has ever sent into space. To understand that journey, we must imagine the vast emptiness between stars. The nearest star system to the Sun, Alpha Centauri, lies about 4.3 light-years away. That distance is difficult to comprehend. A spacecraft traveling at the speed of Voyager 1, the fastest probe ever launched from Earth, would need more than 70,000 years to reach it. Yet interstellar objects like 3 I-Atlas drift across such distances naturally. They are not propelled by engines. They do not accelerate. They simply continue moving with the velocity they were given when they were ejected from their original planetary systems. In the vacuum of space, motion persists. Once an object escapes the gravity of its parent star, nothing slows it down significantly. There is almost no resistance between stars. The density of interstellar space is so low that even over millions of years, it exerts virtually no drag. So when a small body is flung outward by gravitational interactions, perhaps during a chaotic phase of planet formation, it begins a quiet voyage through the galaxy. 3 I-Atlas may have started its journey billions of years ago. Perhaps it formed as a small icy body in the outer disk of a young star system. As giant planets migrated through that disk, gravitational encounters may have thrown it outward. A close interaction with a massive planet could have accelerated it beyond escape velocity. In a single moment, its destiny changed. Instead of orbiting its star forever, it was expelled into interstellar space. The star that once warmed it faded behind, and the object entered a vast cold darkness. Interstellar space is not entirely empty, but it is unimaginably sparse. The density of matter between stars is often less than a single atom per cubic centimeter. Temperatures hover just a few degrees above absolute zero. In that environment, time becomes almost meaningless. Millions of years pass without change. A frozen object like 3 I-Atlas drifts silently through darkness, illuminated only occasionally by distant stars passing across its sky. Cosmic rays, high-energy particles produced by supernova explosions and other energetic astrophysical events, constantly bombard its surface. Over long timescales, this radiation alters chemical bonds within surface materials. Organic molecules can form. Ice structures can change. The surface gradually darkens and reddens. This slow process is known as space weathering. If 3 I-Atlas has been traveling through interstellar space for hundreds of millions of years, its outer layers may have been profoundly altered by this radiation. But beneath the surface, its interior may remain pristine, preserved exactly as it formed around its original star. That interior could contain ancient ices, trapped gases, and minerals that have not changed since the early days of a distant planetary system. In some sense, interstellar objects are time capsules. They carry records of conditions that existed around stars long ago. During its long journey, 3I Atlas would have occasionally passed through regions of the galaxy with slightly higher densities of gas and dust. The Milky Way contains vast molecular clouds, cold, dense regions where new stars are born. Passing through such a cloud could coat an interstellar object with thin layers of dust or frozen molecules. Over millions of years, these encounters accumulate. Each adds subtle layers to the object's surface history. But despite these occasional interactions, most of the journey is uneventful. The object drifts through darkness, orbiting the center of the galaxy along with billions of stars. Our Sun itself moves through the Milky Way at roughly 220 kilometers per second, completing one orbit around the galactic center every 230 million years. An interstellar object like 3I Atlas participates in that same grand motion. It is not stationary relative to the galaxy. Instead, it follows its own orbit around the galactic center, determined by the velocity it acquired when it was ejected. During that journey, it may pass near many stars, but near in astronomical terms still means enormous distances. Even a close stellar encounter might occur at several thousand astronomical units, far beyond the outer edges of planetary systems. Such encounters rarely capture or significantly alter the object's path. Instead, they simply nudge it slightly, changing its trajectory by a tiny amount. Over millions of years, these gravitational nudges accumulate. The object's orbit through the galaxy gradually changes. Its direction shifts, its speed adjusts. Eventually, by chance, its path intersects with a region of space occupied by another star. In the case of 3I Atlas, that star happens to be the Sun. As the object approaches the solar system, the Sun's gravity begins to influence it. From millions of kilometers away, the Sun's pull is extremely weak, but as the object draws closer, the gravitational acceleration grows stronger. The Sun bends its trajectory into a curved path. If the object were moving slowly enough, it might become captured into orbit. But interstellar objects typically move too fast for that. Their velocities relative to the Sun exceed escape velocity even before they enter the solar system. So instead of becoming bound, their paths form hyperbolic trajectories. They approach, they accelerate around the Sun. Then they depart again, forever. From the perspective of the object itself, the solar system would appear briefly as a bright region of sky. The Sun would grow larger and brighter. Planets might appear as faint points of reflected light. Then, after passing closest to the Sun, everything would recede again into darkness. For most of its existence, 3I Atlas has likely known only deep space. Its visit to the solar system is a brief interruption in an otherwise lonely journey. Yet for us, this moment is extraordinary because it allows us to observe an object that formed somewhere else, somewhere beyond our planetary family. The more we study these visitors, the more we realize how common they may be. Astronomers once believed interstellar objects would be extremely rare, but modern surveys suggest they may pass through the solar system more frequently than expected, perhaps one every few years, perhaps even more often. Most simply go unnoticed because they are too small or too faint. But with improved telescopes, the detection rate is increasing. Each discovery helps scientists understand the population of objects drifting through the galaxy, their sizes, their compositions, their velocities. These measurements help answer a deeper question about planetary systems. How much material do they eject during their formation? If planetary systems commonly eject large numbers of small bodies, then the galaxy may contain vast numbers of wandering fragments. Some estimates suggest there could be more interstellar objects than stars in the Milky Way. If that is true, then the space between stars is not empty at all. It is filled with the debris of planetary formation, fragments of asteroids, frozen comets, broken pieces of planetesimals, remnants of worlds that never fully formed. 3I Atlas may be one of those remnants, a survivor of an ancient event in another star system, perhaps once orbiting peacefully within a disk of icy debris, perhaps thrown outward during a violent gravitational encounter. Since then, it has traveled across interstellar space, passing through darkness for ages, until now. For a brief moment in cosmic history, its path intersects with ours, and we notice it. In the next part of this journey, we will explore what happens after 3I Atlas leaves the solar system and how its future path will carry it onward through the Milky Way, possibly for millions of years to come. Every journey through a star system eventually ends. For 3I Atlas, the most dramatic part of its visit occurs near the Sun. When gravity pulls it inward, sunlight warms its surface, and telescopes across Earth focus on it with intense attention. But that moment is temporary. Once the object passes Perihelion and begins to move away from the Sun, the story slowly shifts. The intense sunlight fades, any gas and dust activity begins to weaken, and the long outbound journey begins. At first, the change is subtle. As 3I Atlas moves away from the Sun, its speed remains extremely high. Gravity accelerated it during its inward approach, and now the kinetic energy carries it outward. Even though the Sun's gravity continues to pull on it, the object has more than enough energy to escape. This is the nature of a hyperbolic orbit. Unlike planets and comets that remain bound to the Sun, 3I Atlas will not slow down enough to turn back. Its path will continue outward indefinitely. In the weeks following perihelion, telescopes will still be able to observe it clearly. If a coma or tail formed during the inward journey, those features may still remain visible for a time, but gradually, as solar radiation weakens, sublimation slows, jets of gas diminish, dust production decreases, the coma fades. Eventually, the object will return to looking like a simple point of light again. During this outbound phase, astronomers continue collecting data. In fact, comparing inbound and outbound observations can be extremely valuable. Surface changes caused by solar heating may become visible. For example, radiation and sublimation may strip away dark surface layers that form during the object's long interstellar journey. If that happens, fresher material from deeper layers may become exposed. This can alter the object's color slightly. Spectral measurements taken after perihelion may reveal subtle differences compared to earlier observations. Such changes provide clues about the thickness of the radiation-processed crust and the nature of the underlying material. Another important observation involves dust trails. When comets release dust, some of that material spreads along their orbit. For bound comets, these trails can persist for centuries. But for an interstellar object, the situation is different because its orbit is hyperbolic. The dust released during its passage will also follow hyperbolic paths. Instead of forming long-term streams around the Sun, the dust will disperse outward along with the object itself. In effect, 3I Atlas may leave behind a faint cloud of interstellar debris passing through the solar system. But over time, that debris will also escape. Within a few years, both the object and its released material will be far beyond the reach of most telescopes. As distance increases, brightness falls rapidly. Light reflected from an object decreases with the square of the distance from both the Sun and Earth. So when 3I Atlas doubles its distance from the Sun, it becomes dramatically fainter. Eventually, even the largest telescopes will no longer be able to detect it. At that point, the observational chapter ends, but the physical journey continues. Once it moves beyond the orbit of Neptune, the gravitational influence of the Sun weakens significantly. The object will still feel the Sun's pull, but its trajectory will already be firmly set on an escape path. From there, it will travel outward through the region known as the Kuiper Belt. This region contains countless icy bodies left over from the formation of the solar system. Most of them remain bound to the Sun, but 3I Atlas will pass through this region quickly. It will not remain. Soon after, it will cross the distant boundary known as the heliosphere. The heliosphere is a vast bubble created by the solar wind, a continuous stream of charged particles flowing outward from the Sun. This bubble extends far beyond the orbit of Pluto. It marks the region where the Sun's influence dominates the surrounding interstellar environment. Beyond that boundary lies true interstellar space. Voyager 1 crossed this boundary in 2012. Voyager 2 followed several years later. For 3I Atlas, crossing the heliosphere will represent a return to the environment it spent most of its life in. Cold, dark, nearly empty. But unlike a spacecraft, the object will not send signals back. It will simply continue drifting. Over the coming centuries, its distance from the Sun will grow enormous. In 1,000 years, it will be far beyond the outer edges of the Oort cloud, the distant spherical reservoir of icy bodies surrounding the solar system. In 1,000,000 years, it will be far beyond any region influenced by the Sun at all. At that point, the solar system will become just another distant star behind it. Eventually, its motion will again be dominated by the gravitational field of the Milky Way galaxy. It will continue orbiting the galactic center along a path determined by its velocity and the mass distribution of the galaxy. During this long journey, it may pass near other stars, not close enough to collide, but close enough for gravitational interactions to slightly alter its path. Each encounter adds a small change to its trajectory. Over millions of years, these small gravitational nudges accumulate. They gradually reshape its orbit around the galaxy. Perhaps one day, far in the future, its path will intersect with another planetary system, another star, another set of planets. If the conditions are right, that star's gravity will bend its path just as our Sun has done. It may swing around that star once before continuing onward again. And if that star happens to host an intelligent civilization with telescopes scanning the sky, they might notice it. They might observe a faint object on a hyperbolic trajectory. They might realize it does not belong to their planetary system. and they might study it with the same curiosity we now bring to 3-eye atlas. In this way, interstellar objects are travelers not only through space, but through multiple star systems. They connect distant regions of the galaxy. They carry fragments of one system into another. And although they rarely interact strongly with planets, their presence reminds us that planetary systems are not isolated. They exist within a shared galactic environment. As 3-eye atlas departs our solar system, the scientific value of the data we collected remains. Astronomers will analyze its orbit in detail. They will refine estimates of its composition and structure. They will compare it with previous interstellar objects. And when the next visitor arrives, perhaps years or decades from now, they will compare it with 3-eye atlas as well. Gradually, a picture will emerge, a picture not just of one object, but of an entire population drifting between stars. Some will be icy, some rocky, some perhaps fragments of larger bodies. Each will carry clues about planetary systems beyond our own. In time, we may learn where most interstellar objects originate. We may learn how planetary systems evolve. We may even learn how common certain types of planets are, simply by studying the debris they eject. For now, though, 3-eye atlas is already beginning its departure. It came from the darkness between stars. It passed briefly through our solar system, and soon it will disappear back into that darkness again. But the story it tells will remain with us, because every interstellar visitor reminds us of something profound. Our solar system is not alone. It is part of a galaxy filled with countless other systems, each with its own history, its own planets, and its own fragments wandering through the cosmic ocean. When astronomers first confirmed the existence of an interstellar object passing through the solar system, it changed something fundamental about how we see the galaxy. For centuries, scientists assumed that the solar system was largely isolated. Planets orbited the sun. Comets occasionally arrived from distant reservoirs like the Oort cloud. Asteroids wandered through the inner regions. But everything belonged to the same family. Everything formed from the same cloud of gas and dust that created the sun. Interstellar objects break that assumption. They prove that material from other planetary systems can cross the vast distances between stars and briefly enter our neighborhood. 3-eye atlas is one such traveler, and with every new visitor, astronomers gain a rare opportunity to study fragments of distant worlds. The significance of this is difficult to overstate. Most of what we know about planets around other stars comes from indirect observations. Telescopes detect exoplanets by watching for tiny dips in starlight during transits or by measuring subtle shifts in a star's motion caused by gravitational pull. These methods reveal size, mass, and orbital distance, but they rarely tell us what those planets are actually made of. Interstellar objects offer something different. They are physical pieces of those distant systems, fragments of the building blocks that formed planets somewhere else in the galaxy. By studying their composition, structure, and motion, astronomers gain clues about planetary formation processes far beyond the reach of direct exploration. The discovery of 3-eye atlas adds to a growing realization. The Milky Way may be filled with these wandering fragments. In the early days of planetary system formation, enormous amounts of material are scattered outward. Young planetary systems are chaotic environments. Giant planets form within disks of gas and dust, and as they grow, their gravity disturbs nearby objects. Small bodies collide, merge, and break apart. Orbits shift and become unstable. Some objects spiral inward toward their star. Others are ejected outward. Computer simulations of planetary formation show that ejection may actually be common. For every asteroid or comet that remains within a system, several others may be thrown into interstellar space. If this is true across the galaxy, then each planetary system contributes countless fragments to the interstellar medium. Multiply that by hundreds of billions of stars, and the number of interstellar objects becomes staggering. Some estimates suggest there could be trillions of such objects wandering through the Milky Way. Most are likely small, perhaps only tens or hundreds of meters across, but even objects that size can travel enormous distances and occasionally pass through other star systems. 3I Atlas may be one of those fragments. Perhaps it formed as part of an asteroid belt around another star. Perhaps it was once an icy body in a distant cometary reservoir. Or perhaps it is a piece of something larger, the remnant of a collision that shattered a planetesimal long ago. We may never know its exact origin, but by studying its properties, scientists can narrow the possibilities. One of the most important clues comes from velocity. Interstellar objects move relative to the Sun with speeds determined by their motion through the galaxy. By measuring the direction and speed of 3I Atlas, astronomers can determine how it was moving through the Milky Way before entering the solar system. If its velocity closely matches the average motion of nearby stars, it likely originated from a typical star system within the galactic disk. If its velocity is unusual, faster, or from a different direction, it may have been ejected from a different region of the galaxy. This kind of analysis helps astronomers understand how planetary systems distribute material throughout the galaxy. Another clue comes from composition. The chemical makeup of interstellar objects may reveal differences between planetary systems. Our own solar system has a particular pattern of elements and isotopes shaped by the cloud from which the Sun formed. But other star systems formed from different molecular clouds with slightly different chemical compositions. By studying spectral signatures in objects like 3I Atlas, astronomers may detect subtle differences in chemical ratios. These differences could reveal whether the object formed around a metal-rich star, a younger star, or perhaps even an ancient stellar population. Such information connects planetary science with galactic evolution. Interstellar objects may carry clues about star formation environments across the Milky Way. Another fascinating possibility involves organic molecules. Complex carbon-based compounds have been found in meteorites, comets, and interstellar clouds. Some of these molecules are considered precursors to life. If objects like 3I Atlas contain similar compounds, it suggests that the building blocks of organic chemistry may be common throughout the galaxy. This does not mean life is widespread, but it indicates that the raw materials for life may exist in many planetary systems. Some scientists even speculate that interstellar objects could transport organic molecules between star systems. During the early history of a planetary system, fragments ejected into space could potentially carry organic materials far beyond their original environment. If such fragments later pass through another young planetary system, they might deposit those molecules there. Over billions of years, such exchanges could occur many times across the galaxy. This idea remains speculative, but interstellar objects provide a mechanism by which such transfers could occur, regardless of whether that process plays a significant role in the development of life. It highlights the dynamic nature of our galaxy. Stars form, evolve, and interact within a shared environment. Planetary systems eject debris. Fragments wander between stars. Occasionally, those fragments enter another system, and sometimes intelligent observers notice them. 3i Atlas is one such moment of observation. For a brief time, humanity has the opportunity to study a traveler from another star. We can measure its motion. We can analyze its light. We can compare it with objects formed around our own sun. Each new measurement adds a small piece to a much larger puzzle. A puzzle about how planetary systems form, evolve, and interact within the Milky Way. As detection methods improve, the number of known interstellar objects will grow. Future sky surveys will likely discover many more. Some may resemble comets like Borisov. Others may resemble asteroids. Some may be fragments of larger bodies, and each will carry information from another star system. In the coming decades, interstellar objects may become a regular part of astronomical research. Instead of studying distant planets indirectly, scientists will analyze fragments of those systems directly as they pass through ours. And with enough discoveries, we may begin to understand the diversity of planetary systems across the galaxy. 3i Atlas is not just a curiosity. It is part of a much larger story. A story about the movement of matter between stars. A story about how planetary systems scatter debris into interstellar space. And a story about how, once in a while, those fragments pass close enough for us to see them. In the final part of this journey, we will step back and look at the broader perspective. What interstellar visitors ultimately reveal about our place in the galaxy and how they change the way we think about the solar system itself. For most of human history, the solar system felt like a closed world. The sun stood at the center, surrounded by planets, moons, asteroids, and comets, all belonging to the same ancient family. Everything seemed connected to a single origin, a swirling cloud of gas and dust that collapsed more than 4.5 billion years ago to form our star and the planets around it. For centuries, astronomers believed that whatever objects traveled through our skies must have originated here. Even the most distant comets, with their long and mysterious orbits, were still thought to belong to the sun's extended domain, a vast spherical cloud of icy bodies known today as the Oort cloud. But the discovery of interstellar objects has quietly changed that view. The solar system is not isolated. It is part of a dynamic galactic ecosystem. Matter moves between stars. Fragments of distant planetary systems travel across the Milky Way, sometimes for hundreds of millions or even billions of years before encountering another star. Objects like 3i Atlas are proof of that cosmic exchange. They are messengers from distant planetary systems, fragments of worlds we will never see directly. And every time one passes through our solar system, it reminds us that our planetary neighborhood is not sealed off from the rest of the galaxy. Instead, it is connected to it. A galaxy filled with planetary debris. The Milky Way contains between 100 and 400 billion stars, Around many of those stars are planetary systems, some similar to our own, others radically different. Over the past 3 decades, astronomers have confirmed more than 5,000 exoplanets orbiting distant stars, and these discoveries suggest something remarkable. Planets are not rare. They are common, extremely common. Many stars likely host multiple planets, asteroid belts, and cometary reservoirs. But planetary systems are not calm places during their early years. When planets first form, their orbits shift and change. Massive planets migrate inward or outward through the protoplanetary disk. Smaller bodies collide and scatter. Gravitational interactions can fling asteroids and comets into chaotic trajectories. Some of those objects fall into their host star. Some collide with planets, and many are simply thrown out of the system entirely. These ejected bodies become interstellar wanderers, tiny planetary fragments drifting through the dark between stars. Our own solar system likely contributed to this process. During the early era of planet formation, the giant planets, Jupiter, Saturn, Uranus, and Neptune, reshaped the architecture of the solar system. Their gravitational influence scattered enormous numbers of small bodies outward. Some became part of the Kuiper belt. Others formed the distant Oort cloud, but many were ejected completely, sent into interstellar space at speeds fast enough to escape the sun's gravity forever. That means pieces of our solar system are currently traveling through the galaxy right now. Asteroids, comets, fragments of ancient collisions, each one drifting through the Milky Way like a silent messenger. And the same thing has happened and continues to happen around billions of other stars. If every planetary system ejects material during its formation, the galaxy should be filled with these wandering fragments, and that appears to be exactly what we are beginning to observe. The invisible population of interstellar objects. The discovery of 3I Atlas suggests something profound. Interstellar objects are probably far more common than we once thought. The reason we only discovered them recently is simple. They are incredibly difficult to detect. Most interstellar objects are small, perhaps only a few hundred meters across. They reflect very little sunlight, and they move quickly through the solar system, often passing through the inner regions in a matter of months. For most of human history, our telescopes simply were not capable of seeing them. But modern sky surveys have changed that. Powerful automated telescopes now scan large areas of the sky every night, searching for moving objects. Systems like the Atlas survey, Pan-STARRS, and future observatories like the Vera C. Rubin Observatory are designed to detect faint, fast-moving bodies. With these tools, astronomers expect to discover many more interstellar objects in the coming decades. Some scientists estimate that millions of interstellar objects may pass through the solar system every year. Most are too small to detect, but occasionally a larger one, like 3I Atlas, becomes visible, and when it does, astronomers across the world rush to observe it, because every interstellar object carries information about a distant planetary system. Learning from cosmic visitors. Studying interstellar objects offers something that astronomers rarely get: direct samples of other star systems. Normally, when scientists study distant planets, they must rely on indirect observations. They measure starlight. They analyze tiny dips in brightness. They detect subtle gravitational effects. These methods reveal the existence of planets, but they rarely tell us exactly what those planets are made of. Interstellar objects provide a different kind of evidence. They are actual physical pieces of those distant systems, fragments of their building blocks. By analyzing the light reflected from an interstellar object, astronomers can learn about its composition. Spectroscopy reveals the chemical signatures of different materials: water ice, carbon compounds, silicates, metals. If an interstellar object behaves like a comet, scientists may detect gases released as it approaches the Sun. These gases can reveal the presence of molecules like water vapor, carbon monoxide, methane, or ammonia. Each molecule tells a story about the environment where the object formed. Cold outer regions of planetary systems produce different chemical compositions than warmer inner regions. By studying these details, astronomers can begin to reconstruct the object's history, where it formed, how it evolved, and how it was ultimately ejected from its home star. Objects like 3I Atlas therefore act as cosmic time capsules. They preserve information about the early stages of planetary formation, not just in our solar system, but across the galaxy. Could we one day visit one? As the number of detected interstellar objects increases, scientists are beginning to consider an extraordinary possibility. What if we could send a spacecraft to intercept one? Such a mission would represent the first direct exploration of material from another star system. But it would be extremely difficult. Interstellar objects move fast, very fast. When they pass through the solar system, they typically travel at speeds of tens of kilometers per second relative to the Sun. By the time astronomers detect them, they may already be on their way out of the solar system. Launching a spacecraft fast enough to catch up would require advanced propulsion systems. Nevertheless, mission concepts have already been proposed. One idea involves placing a spacecraft in a waiting orbit, ready to launch toward the next detected interstellar object. Another concept involves extremely fast probes using solar sails or advanced propulsion technologies capable of reaching high speeds quickly. Such missions remain theoretical for now, but the scientific value would be enormous. A spacecraft could analyze the object's surface directly, measure its composition, study its structure, and perhaps even collect samples. It would be humanity's first physical encounter with material from another planetary system. Interstellar exchange. Across the galaxy, the existence of interstellar objects also raises fascinating questions about how material moves across the galaxy. Over billions of years, planetary systems have been exchanging debris. Fragments ejected from one star may eventually pass through another. Some may even become temporarily captured by a star's gravity. In rare cases, a fragment from another system might collide with a planet. That means pieces of distant worlds may have already reached our solar system long ago, and pieces of Earth's early history may now be drifting through the galaxy as well. This cosmic exchange suggests that planetary systems are not completely isolated. They are part of a vast galactic environment where matter can travel enormous distances, and occasionally those journeys bring fragments of other systems into our reach. The possibility of organic molecules. One of the most intriguing aspects of interstellar objects involves organic chemistry. Complex carbon-based molecules have been detected in interstellar clouds, comets, and meteorites. Some of these molecules are considered precursors to life. If interstellar objects contain similar compounds, they could play a role in distributing organic materials across the galaxy. This idea is sometimes connected to a concept known as Panspermia, the hypothesis that the building blocks of life, or even microbial life itself, could be transported between planetary systems by natural processes. Most scientists remain cautious about this idea, but the presence of organic molecules in comets and meteorites shows that complex chemistry is not rare in space. If interstellar objects carry similar compounds, it suggests that the ingredients for life may be widespread across the galaxy, our solar system as part of a larger story. The discovery of objects like 3I Atlas reminds us that our solar system is not unique. It is one planetary system among billions. It formed within the Milky Way's vast disk of stars, gas, and dust, and like other systems, it has been shaped by gravitational interactions, collisions, and cosmic events over billions of years. Interstellar objects are part of that story. They are fragments of planetary formation, pieces of distant worlds scattered across the galaxy. Most pass unseen through the darkness between stars, but occasionally one crosses our path, and when it does, it offers a rare opportunity to study the broader processes that shape planetary systems everywhere. The beginning of a new field of astronomy. When the first interstellar object was discovered in 2017, astronomers were surprised. Now, less than a decade later, interstellar astronomy is becoming a new field of research. Every new detection adds data. Every observation improves our understanding, and every object reveals something new about how planetary systems evolve. In the coming years, new telescopes will dramatically increase the number of discoveries. The Vera C. Rubin Observatory, for example, will scan the entire visible sky every few nights, detecting faint moving objects with unprecedented sensitivity. With such instruments, scientists expect to discover dozens of interstellar objects every year. Some may be comet-like, some asteroid-like, some may even show completely unexpected properties. Each one will help answer fundamental questions. How common are interstellar objects? What are they made of? Where do they originate? And how do planetary systems across the galaxy evolve over time? A moment in human history. For most of Earth's existence, interstellar visitors pass through the solar system unnoticed. Dinosaurs never knew they were here. Early humans never saw them. Even the greatest astronomers of the past, Galileo, Newton, Kepler, lived in an era when detecting such objects was impossible. But today, we live in a time when the technology exists to find them. We can detect faint moving objects millions of kilometers away. We can measure their speeds and trajectories. We can analyze the light they reflect. For the first time in human history, we can identify travelers from other star systems. And that realization carries a powerful perspective. The solar system is not a closed island in space. It is part of a vast galactic network of stars and planetary systems. Matter moves between them. Fragments travel across unimaginable distances. And occasionally, those fragments pass close enough for us to notice. The quiet passage of 3. I, Atlas. 3. I, Atlas will not stay long. Like other interstellar visitors, it will continue its journey. It will pass through the solar system only once. After its brief encounter with the Sun, it will accelerate back into interstellar space, never to return. In a few years, it will fade into darkness, a tiny fragment of another star system drifting once again between the stars. But during its short visit, it offers something extraordinary, a reminder that the galaxy is alive with motion, a reminder that planetary systems are connected, and a reminder that even small objects, a fragment of rock or ice, can carry stories that span the entire Milky Way. Looking up at a larger universe, when we look up at the night sky, the stars appear distant and unchanging. But the discovery of interstellar objects reveals a hidden dynamic universe. Stars move through the galaxy. Planetary systems form and evolve. Fragments of those systems travel across the interstellar void, and sometimes those fragments arrive here. Visitors from distant stars, messengers from worlds we may never see, each one reminding us that our solar system is only a small part of a vast cosmic story, a story that stretches across billions of years, across billions of stars, and across the entire galaxy. And perhaps as our technology improves and our understanding grows, the next interstellar visitor will not simply pass by unnoticed. Perhaps one day, humanity will be ready to meet it, to study it up close, and to learn directly from a traveler that began its journey around another sun. Until then, objects like 3i Atlas remain rare and fleeting guests. But their existence changes how we see the universe. They remind us that space is not empty. It is a vast ocean of motion, filled with travelers moving silently between the stars. And sometimes, just sometimes, one of those travelers passes through our cosmic neighborhood, allowing us to glimpse a piece of another world.